Hey everyone, today we're going to dig into this incredible, almost forgotten idea from nearly 100 years ago. It's called the calculus of intervals, and trust me, it's going to make you rethink the very basics of what a number even is.
So let me just start by asking you a question. What if this whole concept we have of an approximate number is basically a myth? What if the way we all learn to deal with uncertainty in our calculations is, well, fundamentally wrong? And you know, this isn't some newfangled problem. It turns out that way back in 1928, a mathematician named A.K. Suskovich published this one single article that proposed a totally radical answer to that exact question.
Okay, so first things first, let's really nail down the problem with approximation itself. Because to really get why Suskovich's idea was so brilliant, you have to understand the challenge he was up against.
And the problem is something we all kind of know, right? I mean, every single time you measure something out in the real world, like the length of a table or the temperature outside, you are never, ever perfectly exact. There's always this tiny bit of uncertainty, and that little bit of fuzziness can cause huge headaches when you start doing math with it.
And this is where our guy, Anton Kazimirovich Suskovich, steps onto the scene with his pioneering idea, a concept that was just decades ahead of its time.
So get this, Suskovich published his paper in 1928. But the whole field we now call interval analysis didn't really get going until the 1950s. He was so far ahead of the curve, and today, his ideas are literally foundational to how modern computers handle calculations where nothing is perfectly certain.
So what was this big idea? It's captured perfectly right here in this quote. He basically said, the truly approximate value is nothing more than an interval. Now, that might not sound like much, but this wasn't a small change. It was a complete 180-degree shift in thinking.
You see, the old way of thinking about an approximate number was kind of vague, right? It was this fuzzy point with some error around it. Suskovich just said, forget that. Instead of a fuzzy point, let's treat the entire range, the interval from point A to point B, as the actual real mathematical object. It's not vague at all. It's perfectly mathematically rigorous. So, this leads to a whole new kind of arithmetic. I mean, if these intervals are new numbers, how in the world do you actually do math with them?
Now you're probably thinking, okay, that's cool for measurements, but what about an exact number, like 3? Suskovich had this super elegant answer. An exact number is just a special type of interval he called a degenerate interval. It's where the start and end points are the exact same. So the number 3 just becomes the interval 3, 3. And just like that, everything, exact numbers and approximate ones, can live together in one beautiful system.
And when you start doing calculations, this is where the magic happens. Let's say you measure one thing, and you know it's somewhere between 2 and 3. And you measure another, and it's between 4 and 5. When you add them together, the result is a new interval that expands to include every possible outcome. So in this case, it becomes 6, 8. This creates a guaranteed boundary. Yeah, the range might get a little wider, but you know with 100% certainty that the true, perfect answer is somewhere inside.
And that right there brings us to the real superpower of this whole thing, the power of guaranteed boundaries. Why is this abstract math idea so incredibly useful in the real world? Because this is the biggest payoff of his entire theory. You get a guaranteed box that you know contains the precise answer. Think about it. With normal math, tiny rounding errors in a computer can add up and up and up until your final answer is just totally wrong. With interval arithmetic, you have a mathematical promise that the true value is always safely inside your final range, no exceptions.
And you can literally draw a straight line from his 1928 paper to today. His calculus of intervals became what we now call interval analysis in computing. His idea of the expanding interval is now the whole basis for guaranteed problem solving in really critical software. It even affects how computers store numbers in memory, and it's helping us build new kinds of logic to deal with vagueness.
So yeah, this one idea created a massive ripple effect that's still going. Let's wrap up by looking at Suskovich's incredible, lasting legacy. So if you remember anything from this, here are the big things. 1. Approximate values aren't fuzzy numbers, they are precise mathematical things called intervals. 2. This simple switch lets us get guaranteed answers in really complex calculations. 3. It gave us a whole new formal language to talk about things that are vague or imprecise. And 4. It built this amazing bridge between the messy real world of measurement and the super clean world of formal logic.
And the impact goes even deeper, into philosophy, actually. By giving us a solid way to handle imprecision, His work helps us untangle some really tricky paradoxes that pop up because we can't measure things perfectly. It helps answer a really profound question. How can we think logically about a world that we can only see imperfectly?
Which kind of leaves us with this one last, pretty mind-bending thought to chew on. If Suskovich was right, if every single measurement we take, every piece of data we collect about the universe is fundamentally an interval and not a perfect point, then how certain can we really truly be about anything?